Today we're going to be answering the question, how do computers work? In order to answer that, we have to differentiate the two answers that I came up with. I'll name them right now. There is the software answer and there's the hardware answer. And they both work. Now, in order to understand why they both work, we have to talk about something called abstraction. Abstraction just generally can be defined as how much information do you need to have in order to do something. Now, I'll give you an example. If you are turning on your car, and in order to do that, you put the key in the ignition, you turn on the car, and that's it. That's a relatively high amount of abstraction, because you're not interacting with the thing that starts the car. You're interacting with the key. But if you were to crank the starter motor, then you would be interacting with the thing that starts the car, and you would have a relatively low amount of abstraction. Now, let's talk about this computer level hierarchy. There is a hardware level, which is below the software level, which means that the software is directly reliant on the hardware. You cannot have software without hardware, but you can have hardware without software. Do keep in mind that whenever you're making software or hardware, you do have to be thinking about either one to a certain degree. It's not too much, and it is depending on the context, but generally it's not too much. Let's talk about the programming answer. And what that means is, how can we answer how does a computer work with the program? And the answer to that question is, well, it works in the way you tell it to. In this Python program, for example, we tell the program, okay, get a number from whoever is typing it out, and then print that number out. And if you run it, as it was done here, that's what happens. It's not a super complicated thing. Now, this program has a lot of abstraction. It doesn't really explain how what is happening works under the hood. And if you want to know that, we'd have to move to something that has lower abstraction, like C. Now, for our purposes, the main way that C adds abstraction is by making it giving you a little bit more freedom to handle how you look at variables. And that isn't really explaining a lot. It doesn't explain what $x as a reference is. Doesn't explain a lot, but it'll be just a general explanation. We won't look at C too much. Now, if you look at the program, it does pretty much the exact same thing. And even still, those 8 lines of code don't really tell you how it works, or how the computer prints a number and gets the user input. Now, if we move to something called assembly, which assembly is the second to lowest level of abstraction you can have. The first level is called machine code, which is, you'll think of it as a binary or zeros and ones or an exe file. Now, if we run this program, it doesn't take a number. That's kind of hard with this program, or with this language. But it does print it out, and you can say over there where it says move EAX, comma, space 35H, and then takes in the number. You can change that takes in the number, and that will change what the number printed is. But even that doesn't fully explain how your computer prints out the number or takes in the user input. And there are a couple complicated things that go into it. This assembly program shows the registers being moved and memory being moved and blah blah blah. And it shows a little bit of how the operating system is handling it. But it doesn't give a full explanation as to how every single part of the computer is coming together to do the thing that we want it to do. Now we've seen a little bit of software level abstraction where we didn't really much care about the hardware, but we can contrast that with hardware level abstraction where we don't really care about the software. Computers today are made up of what's called digital circuits, but they're still reliant on analog circuitry. Uh, dig- you can see a little example of a DC sweep or a digital current sweep over here. We're mostly going to be talking about digital circuits going forward, but you might have heard the phrase that computers are made up of zeros and ones. That's a half-truth. It's more descriptive to say that computers today are made up of high voltage ranges and low voltage ranges, where the high voltage range is a 1 and the low voltage range is a 0. And then just moving on from that, the smallest component of a computer is a transistor. Or that's half truth. Really, it's like the one we care about. You could go deeper with components of a transistor, but for the ones we care about, for our purposes, the smallest component of a computer is a transistor. And then modern computers are made up of billions of them, like actual big B billions of them. And thanks to something called Moore's law, the number of transistors in a computer doubles every 2 months, or sorry, every 18 to 24 months, not every 2 months. And then there's two main types of transistor that we'll be talking about. There are other types. There's a lot of other types, but two main sort of types that we'll be talking about, and the subtypes. And there is two different subtypes that we're talking about, but these are two main types. And those are bjts, which is a bipolar junction transistor, BJT, and fets, which is field effect transistor. And we're going to be looking at fets, but but among fets there's JFETs and MOSFETs, or junction field effect transistor and or metal oxide semiconductor field effect transistor. We're going to be looking at MOSFETs. We want to look a little bit more at MOSFET. We want to be looking a little bit more at MOSFETs, but let's just get a little higher level overview of why we're looking at them. BJTs generally, this is not universally true, but generally are better for analog circuits. FETs are generally better for digital circuits. And then, so among MOSFETs, there is once again JFETs, which is junction field transistors, and MOSFETs. And then there's two subtypes again, which is the enhancement mode and the depletion mode MOSFET. We'll be talking about the enhancement mode. The only real difference between these is that an enhancement mode is off by default and the depletion mode is on by default. Enhancement mode is the one we're going to be talking about because you would think it's more power efficient, which modern computers are going to need. And then inside of enhancement mode, there's a P channel and an N channel. Going forward, we'll call this PMOS and we'll call this NMOS. Whenever PMOS and NMOS are used together in complement to make what is called a complementary metal oxide semiconductor, or CMOS. That's where you've probably heard that term before if you're coming into something like this, but that's where CMOS comes from. CMOS does use both of them. That doesn't necessarily mean that CMOS is the only logic that uses both of them, but yeah. And then just to restate it, there's two main different types of transistors that we were looking at. We're going to be looking at MOSFETs, which is a type of FET, in the enhancement mode, which means that it's off by default. And we're looking at both PMOS and NMOS, which uh, which you use them together to make CMOS. All right, for digital logic, we can think of MOSFET as a voltage controlled switch, which basically means that it is controlled by the voltage. So you have to give it an input voltage, and then you'll get an output voltage. Now, once again, remember that there's two different real types of transistors that we'll be talking about, which is the NMOS and the PMOS. And they work in exact opposites. which is sort of expected, but you know. Now the NMOS, it turns on whenever you give it a 1. So if the input is a 1, then the NMOS will turn on. PMOS, exact opposite. If the input is a 0, then the PMOS turns on. And let's just look at that with a simple inverter over here. If this inverter is given an input of a 1, it'll go to both of these, and the PMOS will turn off, because remember, whenever an input of 0 is given to the PMOS, then only it turns on. So PMOS doesn't turn on. But whenever an input of 1 is given to this NMOS, it does turn on, and then the voltage goes to ground. And by doing that, there's no output voltage here. So this is a 0. So it was originally a 1, and then it became a 0, right? And that's how inverters work. They take whatever your input is, they opposite it, right? So if it's a 1, it's now a 0. But if it was a 0, it's now a 1. Let's look at that from a 1. The input is a 1. It'll once again go to the inverter, and the inverter says, or sorry, let's look at it from a 0. It goes to the inverter. Inverter is a 0, or sorry, the NMOS is a 0. It doesn't turn on. It goes to the PMOS. PMOS does turn on, and what happens is the source or the VDD or whatever you want to call it. Here it's written as plus 5 volts. Will flow from the plus 5 volts, the VDD or the source, to the output and make the output a 1. And that's just the basics of how an inverter works. And the sort of mapping of how a logic gate maps to its inputs to its outputs, as in how it responds to them, is called a truth table. And a truth table is generally used with logic gates. And what is a logic gate? This is a couple of logic gates, and all that a logic gate is a collection of transistors in a certain way so that it makes a certain truth table. And I'll give you a sort of an example. An AND gate, an AND gate, whenever you give it both terminals, or both inputs are 1, the output is 1 as well. No other input, or no other output is a 1, given inputs of just a 1 in a single terminal, or a 0 in both, or a 1 in the second terminal. Now, if you have a 1 in both input terminals, then only will you get an output of 1. And that's how the AND gate logic or truth table works. NAND is the exact opposite. You'll look here, 0, 0, 0, here is 1, 1, 1, and then here is 0, here is 1. So a NAND is literally just an AND gate with an inverter strapped on. Now the implementation isn't guaranteed to be like that. You can probably do it in a different way, but you get the idea. Alright. And just to make it abundantly clear, this is the AND gate, this is the NAND gate. You might notice the difference in naming is that an N was strapped on to the beginning of that. So you can think of it as a not and. And here is an or and a not or, right? And all that does is it inverts the behavior of the truth table. So you'll take the truth table of an or, and you'll say, is the output a 0 or a 1? Is the output a 0 or a 1? And you'll switch it. So here it's a 0, now it's a 1. Here it's 1, 1, and 1. Here it's 0, 0, and 0. Alright. Now, in this video, we've talked about like all sorts of abstraction, but we talked about specifically from the perspective of software versus hardware abstraction, just a little bit, not too far in depth. We saw a simple C file, a Python file, and an assembly file do almost the same thing. The assembly file didn't do the exact same thing as the others, but the C and Python file did the same thing, and we saw them do it at a little different level of abstraction, which meant that we had to interact in different ways with the programming language in order to do the same thing in our case. And we talked a little bit about transistors and how they relate to digital and analog circuits. Not too much about analog, but we did cover it a little bit. And then we talked about fets and how we will be using CMOS, which is made up of PMOS and MOS. And we talked about sort of the different transistors in between that. We talked about all these logic gates and how the truth table is sort of the way that logic gates are shown to like function, as in the reason or any logic gate that has this truth table is an OR, right? It's basically an OR. If it has two inputs, one output, and these are its inputs and outputs, or if you can make this table the input and output, it's an OR gate, right? That's what makes up an OR gate. Is this symbol is how we demonstrate it, but this logic gate, or sorry, this truth table is really what makes up an OR gate.